Hi everyone. So in this video we are going to see a new lead code problem, which is lead code 75. Actually, it's under lead code 75. So this is the problem statement. So we have to search in a binary search tree. So let's see what is binary search tree first. It's actually a tree where we have node. This is the root node, and from there we will have the child nodes. So the left child will be lesser to the root node, and the right child will be greater than the root node. Similarly, for each node, the rule applies the same. So the left child will be lesser than the root node, and the right child will be greater than the root node. So that is how the values are stored inside a binary search tree. So let's see the problem statement. So you are given the root of a binary search tree. So this is the root. In our case, 4 is the root and an integer value. So integer value can be anything, 1, 2, 3, any integer value. Find the node in the binary search tree that the node's value equals value. So integer value we have, right? So that value should be equal to the value of the node present in the binary search tree. So that is what this statement means, and return the subtree rooted with that node. So if we have found that particular value which matches to that node, we have to return the subtree associated with that node. Let's take an example of 42713 and the value is 2. So in this case, 2 is the value which we have to find in the binary search tree, right? So we have found 2, and we have to return all the elements under it, all the subtree under it, like 2, 2 has 1 and 3. If 1 again has subtree, then we have to return that also. That's how we have to find the particular value in the binary search tree. So let's see how to write the code for this. Already we have a class which is already defined in this lead code problem, and this has a tree node, and the tree node actually has a value, and it has a left and it has a right. Left is nothing but the left node, and the right is nothing but the right node, and the value is nothing but the value inside that nodes. So we will try to solve it one by one. Let's take the base case first. So if root equal to null means which is the base case, so directly I will return as null, because if the root is null, which means we don't have any elements to traverse, right? So directly we will return null. Then we will check if root dot value equal to value, which means let's say our value is 4, and if that 4 equals to this root itself, then we will directly return that root itself. So it will return all the subtrees under that root. So that's how we can think of the if statement. Then again, one if statement we have to write. We have to check if the value is greater than root dot right. So let's say we have a value called 5 here. Let's not take this example. So let's imagine that we have to search 7. Okay, so 7 value is greater than the root actually. So the 7 value is greater than the root. If the value is greater than the root, what we have to do? We have to make that root to point to the right of the root. Root is equal to root dot right, because the greater element is present in the right side of the root, right? That's why we have to make that root to point root of right. Then we again have to recursively search using search BST function itself, because why we need recursive function here? Because there are multiple subtrees under that particular tree, right? We have a root and we have a value, so there can be multiple subtrees. So till we have arrived to that base condition, if root dot value is equal to val or root is equal to null, uh, till that we have to recursively search under that binary search. That's why we have to do this recursive operation. Then we have to check if value is less than the root. The same thing, I'm going to just make that root point root dot left actually. Then again the search, same recursive function I will apply, root dot val. Then finally I will return, if all the cases we have finished, finally I will return null if nothing is found. So that's it. Let's see whether this is solving our problem. Okay, we have some issue here. Okay, I'm comparing the value with the root. Root is actually a true node, so we have to do root dot value. That's my state. So again, root dot value here, root dot value already have put here, so this is fine. Let's run and see our code. Yeah, it's accepted. Let's submit our code and see. Yeah, so the runtime beats 100% and memory beats 74%. So which means it's good in terms of time and space complexity. That's it, guys. This is how you can search a particular value in a binary search tree.